since we've actually done some formal notes and things like that, and that's what's going to happen for most of the day today. You have not had any book homework for a while either, and so I promise, because I don't want you to be sad, I don't want you to be feeling like your kind of overarching routine has gone by the wayside. This is actually going to be homework for tonight, because I looked at it and you could have done it last night.
Yes.
Sorry. Except for, I guess there were a couple. We're going to finish it. We'll get you where you need to go for tonight. So anyway, homework for tomorrow is right there. I have not updated that on Canvas. So if you look on Canvas, look at the homework that is listed for yesterday. Does that make sense? I will try and get it updated to after class, but I just haven't gotten there yet. All right. So the first thing that I need is your pendulum labs turned into me and your graphs for the lab analysis with your determination of what the acceleration due to gravity is. I would like that all put together in a very nice neat pile if you haven't done so already. Pendulum lab, graph, any other explanations?
So, all three of us forgot to do the second part, but we have our first part of the last time.
So give me what you have. All right. It's all good. We'll work it out. All right, friends, so make that happen. I'm going to give you 1 minute, and then I want to move on.
Rudy had another topic.
You have 1 minute. This is not time to do the lab. It's time to turn in the lab. If you're not done with the lab, then you can turn it into me later with a late card.
Yeah.
This one, then this one. Just like that. Stay both together.
I have some book.
That's fine.
Yes.
So pendulum lab, graph, any extra work. Pendulum lab, graph, any extra work. All right. So, physicists, we're going to go ahead and start, which means that you need to be seated. You need to be ready to go. We are today going to define SHM. What is that? That's a good question. If you don't remember, we talked about it a little tiny bit a couple days ago, but let's actually put a definition to it. This unit is all about a certain kind of motion. So your notes are out because we're going to start writing stuff down in just a moment here. Okay, it's all about a certain kind of motion. That kind of motion is called simple harmonic motion. Okay? Simple harmonic motion. My claim to you is that pendulums exhibited simple harmonic motion. You just smiled and said okay, because you had no reason to doubt me. And we'll see how that feeling feels for the rest of the day today and for the next couple days going forward. Right now, though, we're just going to talk about what this thing may very well mean. What does the word simple mean? Easy, right? Easy, or maybe not complicated. Absolutely. Is there complex harmonic motion? Absolutely there is. Are we going to study it in this class? No. We're not going to get to the complex stuff. We're just going to keep it simple. Okay? Simple harmonic motion. I'm going to skip the harmonic for a minute and talk about motion. What is motion? I think we can probably figure that one out. Movement, right? Objects that are not sitting still. Okay, so we got some movement. This word in the middle is the one that we may or may not know the definition to. Have you heard the word harmonic before?
Yes, it's an instrument.
A harmonica? Sure. You've also heard, what did you say, Kate? Harmony?
I think harmony.
harmonize, all of those. What is harmonic?
Oh, I had a question.
Go ahead.
Is dampened harmonic motion a form of complex harmonic motion, or is it a form of simple?
Both simple and complex harmonic motion can be damped. So that's a whole so dampen basically just means friction. Add friction to the system.
Oh, that's why we did it. We did it pre-cover.
Yeah. So that's why.
That makes
Yeah. So the dampen thing is just is there friction or not? Yes. Yeah. All right. What does the word harmonic mean? Have you heard of it in other things? Do I have any musicians out there? Is there any music theory kind of people? What are harmonics? Do you know?
What?
What are harmonics?
Phrases.
Sound waves. I like the sound waves. Something.
Yeah.
Stop telling Harrison.
Yeah. I don't often say what Henry says, but I'm going to say it this time. Stop telling Harrison and tell all of us. What'd you say?
I don't know. It's like how the sound waves mesh together in the right way. I don't know really anything about that, but yeah.
That seems like a reasonable statement. It's how the sound waves, that's the key word that I wanted there, sound waves mesh together to sound nice, right? So if you're a musician and if you start taking and thinking about music theory, a lot of what they talk about, you can play two notes that will sound very nice together. You can also choose two notes that do not sound nice together. And the ones that sound nice are called harmonics, right? And there are different kinds of harmonics, and they're all, there's tons to that. We're not going to get into that right now. But the key here with all of that stuff is that we're talking about waves, and even a little bit less technical than waves, we're talking about things bouncing or oscillating, okay? Objects oscillating. Isn't it always nice when you try and define a hard word with another hard word? What does oscillating mean? You can all do the dance, right? Right, go up and down, move up and down, go from one side to right. That is an oscillation. The application of pop culture right there. Okay. If an object, bless you. If an object is exhibiting simple harmonic motion, and to be clear, not all objects that oscillate exhibit simple harmonic motion. That's the trick here, okay? The things that exhibit simple harmonic motion have a very, very specific, they fit a specific definition. And the definition is that the object's motion must be a result of a force that is, oops, that's not one word, sorry. There are two conditions here. Sorry, I'm trying to make this nice and I am not doing a good job. Force, that is always proportional to the object's displacement from equilibrium. All kinds of good physics words today. And always, I guess I had that right before, directed toward the equilibrium. Okay. That's the wordy version of it. But I want you to know this. I feel like I've seen on old AP Physics 1 tests questions where they say, is this system an example of simple harmonic motion? And the question is basically asking, do the students know that it needs to be proportional to the displacement and always directed toward the equilibrium? So those are going to be some key things that you need to pay attention to. Always proportional to the displacement. Okay, so what does that mean? It's a good question, right? Great question, Ms. Kay. What? I don't know. The force is proportional to the displacement.
Is it like if the displacement increases or decreases, the force also has to increase or decrease?
That's exactly right. Yeah. So let's write that down. So this, if we're going to write this down into some, words or phrases or symbols that make a little more sense, that means that as the displacement increases, the force increases. Similarly, if the displacement goes down, the force has to go down. Okay? And the amount of increase or decrease is dependent on some sort of proportionality constant. Okay? So if x goes up, f goes up, and vice versa. What does this second part mean? It's always directed toward the equilibrium. What's that?
I didn't know, I forgot what was directed toward.
Yeah.
So, like if the force is directed toward equilibrium, then the force is pushing toward the center or something, or toward where it started.
Yeah. So it's always going to push. Come on. Toward, I like kind of saying the center. It's not always a center, but it's always going towards the center. If we were going to take these two big statements or these two littler statements and put them into an equation, something that basically makes all of this true, an object's motion has to be the result of a force that is proportional to a displacement. We mark displacement with an X, right? So it's proportional to a displacement. So it's going to be equal to some constant. I'm going to pick the constant K. Is that okay? Proportional to or the proportionality constant times some displacement. Are you with me there?
Yeah.
Okay. So the bigger X is, the bigger F is. The smaller X is, the smaller F is. And always pushes toward the center. So I'm going to displace something, and I've displaced it in the positive direction. Which way is the force going to pull or push? In the negative direction. And if I displace something in the negative direction, which way is the force going to pull or push? Positive. So what do I need to include in this statement? I have to have a negative sign, right? To make this side and this side always be opposite. Then I'm going to put a box around that. And I'm going to ask you to think back to last year. And by last year, I mean like a month ago, not like 12 months ago. Have you seen that before?
I feel like I have.
I feel like you have too.
Oh, I remember. It's with
I'm just going to give you an air high five for that because I feel like that was awesome.
It's with one of the energies, right?
We did this in order to get to one of the energies. What unit or what kind of energy did we study that before we talked about it? Spring energy, right? Hooke's law. Look at you. This is Hooke's law. So the funny thing about this, you guys, it's really interesting. The last unit, this unit, and then like the next two units, they all kind of build on each other. It's really kind of cool. So we've seen this before. You did this lab already. You already figured this out. But now, instead of, I want to remind you what you did with this lab, because you had the little Hooke's law apparatus, you had the little spring, and you put the mass on there. Do you remember? Then you put a little more mass on there. What happened to the spring?
It bounced.
It did not bounce. We didn't look at any motion with that, did we? We let it sit in equilibrium every time. Do you remember? And we didn't say it super explicitly, I don't think. But so here was the spring, and then you had the mass, and there was a gravitational force, and there was a spring force. And as we pulled this down, equilibrium changed, didn't it? And the force changed with it.
I actually don't remember this. I thought it was the one where you.
I love that you're so honest.
What's the one where you shoot the balls?
That was the.
Ballistic pendulum?
Oh.
Because you were thinking pendulum from yesterday.
Yeah.
We'll get there too. Yeah. I appreciate that. So let's get our brains back to this if we weren't there before. Do you remember now? Does this sound familiar now? You put mass on here? You put mass on here and it stretched some more and mass and stretch and mass. So that one we were changing the F and that changed the X, right? We changed the F and it changed the X. Most of the time when we talk about our simple harmonic motion, we're going to go the other way. So we're going to displace it a certain amount and then we're going to watch it go bouncy, bouncy, bouncy back and forth. Okay? And as it goes bouncy, bouncy back and forth, the force is going to change as a result of the displacement. And the proportionality constant is K. All right? So, given that this is the definition of something that experiences simple harmonic motion, is it fair to say that a mass on a spring would exhibit simple harmonic motion?
Yes.
I think so. I should have gotten one out and we could watch it bouncy, bouncy, bouncy. We'll do that in a couple days. We'll do some actual lab with it in a little bit. But bouncy, bouncy, bouncy is going to exhibit simple harmonic motion because holy cow, it has to do with this. Now, question. Can you think of anything else that might exhibit simple harmonic motion? This is kind of a deep, weird question to ask now, but I'm going to ask it anyway.
Trampoline.
What's that?
Probably not.
Tramps. Leads.
What do you got? What do you think? Trampoline?
That's what I said, but I was just thinking like things that go up and down.
So a trampoline does, right? Now, you have to kind of think about what part of a trampoline, right?
Yeah.
And I'm not a trampoline expert, so I'm just going to put that out there. But when you land on a trampoline, is it exhibiting simple harmonic motion then?
No.
Bouncy, not really. But I think, and again, I'm not an expert, but I think if you jump off of a trampoline, then the actual mat is going to go bouncy, bouncy like this a little bit, right? Yeah, it's dampened, which is why it doesn't just keep doing this forever. But for sure, yes, there is some simple harmonic motion on a trampoline. What else you got? Yeah. What do you mean? So I like that you suggested that. I want to think, I actually want to really think about what happens with a basketball. Because if you watch a basketball, you drop it, and you watch the basketball and it bouncy, bouncy, bouncies, right? So there is some oscillation that happens there, right? But here's my question. Does the force that's pulling or pushing the object back towards equilibrium, does it vary with its displacement from equilibrium?
No.
So what's the object? The object is a basketball?
Yeah.
I want to make sure I'm talking about the
So
system that you're talking about.
If it's once it's going,
So once it's going down.
as it's going down each time, does it vary with what?
With its position relative to equilibrium.
Wait, where would equilibrium be? In the air?
Well, that's a good question too. Equilibrium is where F net equals 0. So on the ground, I would say probably. I mean, the system is kind of hard to define, but let's talk about it. If we talk about the ground being in equilibrium because you've got the floor pushing up and the earth pulling down, so that's equilibrium. As I pull my basketball up, or as I watch my basketball fall, does the strength of the force that's acting on it vary? What force is acting? Gravity, right? So I'm really glad that you brought that up because it does bouncy, 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 and you kind of want it to say that way, right? But in this case, it's not because it doesn't vary with X. Yeah. So thanks for suggesting that, but I'm going to not put that on my list. Yeah.
What is that little thing over there?
That little thing. Which little thing? There are lots of things.
What? Newton's cradle, yeah.
Newton's cradle? Tell me what you mean.
You pull the basketball off.
Okay. So I'm not going to include all these because that gets confusing. But if I include just one, is there a force acting on that ball?
Yes, applied.
Actually, hold on. Let me back up for just a second. Is there an equilibrium position for the ball?
Yes.
Yeah, like right there, right? Okay. So if I displace that ball from equilibrium, like this, right? I'm not very good at doing this with 0 hands. Does it feel a force that pulls it back towards equilibrium? It does. The question is, does that force vary as the distance changes?
No.
The short answer is yes. And we're going to prove it, but we're not going to prove it today. So I'm glad that you brought it up. I'm going to put it on the list, but maybe not in a way that you have in your head yet. But Monday, I think it's Monday, is our big day for pendulums.
So wait, I have a question then. So
Yeah.
basketball, I don't get how the ground is equilibrium.
Well, equilibrium just means F net equals 0. So where is the natural spot for it to be, right? So like somebody didn't clean their pendulum up yesterday, so it's still sitting over on my table. Whatever, I don't care whose it is, it's there, so we can use it as an example. Okay? So there's a pendulum sitting there, is it in equilibrium?
Yeah.
Yeah.
But
So-
I thought that's because it goes both ways on either side of it.
So Kate's gonna displace the pendulum from equilibrium. And then all of that force keeps pulling it towards equilibrium, right?
Okay.
Yeah. And the question is, so this part, I think the negative sign in that statement as to whether or not it's simple harmonic motion makes sense, right? The force is always trying to pull it back towards. This varying part, you may or may not be convinced of. And I'm going to ask that you sharpen your pencils. I think it's going to be on Monday, and we'll actually go through and show that it's true. Okay? But for right now, you're just going to have to take my word for it. Hope that's okay. But yes, a pendulum does exhibit simple harmonic motion. Okay. Anything else that you know of? Yeah. You sure? There's one other one that's kind of a classic example, and again, it's not one that you might think of intuitively, but I've got something kind of similar to it. Can you guys stop talking, please? It's super distracting to me. It's super hard to think and super hard to teach when you're talking. Henry, do you have a question?
Would water be one?
I was thinking that.
You need more like water.
Like if you like.
What does that mean?
Like the way I thought about like if you drop a rock in the water, the water it'll like shoot up, like the stuff will come up, and then it like goes back down to the water.
So water waves do exhibit simple harmonic motion, yes.
I don't think that's what he's talking about.
No, it's
Like a ripple? Is that what you're talking about?
yeah, that's what I'm talking
That, yes.
Alright.
Yeah.
No, guys,
Oh, that's what you're talking about? No.
Nick, what?
Slinky.
A slinky, what do you mean?
That's what
Slinkies do lots of things too.
Just like, like a slinky, like if you like pull it and release it, it'll like.
It goes bouncy, bouncy, bouncy? Yeah, because it's a spring. But you're right, I'm gonna put it on the list too. You're right. It's true. Yeah, I'm gonna put water waves, yeah, just chill out.
I want my name with them.
It's a bouncy, bouncy, bouncy. Yeah. Here's the other one that I want to show you just real quick. So this works also in like any bowl, any kind of rounded bowl. So I'm going to try and do this while I hold it, and we'll see if it works. And I'll tell you more about this curve later. But if you watch carefully, you see how it goes back and forth and back and forth and back and forth? It's kind of like the opposite of a pendulum, right? It doesn't have a string pulling it up, but it's got the surface, like a normal force, pushing it back towards equilibrium, back and forth and back and forth. There's a lot of friction on there, right? Which is why it kind of slows down fast. So it's dampened. But yes, harmonic motion happening there as well. Yeah, because you got a force that changes with displacement, and it's a force that is always pulling it back towards the center. Life is good. How are we feeling? We doing all right? Fantastic. All right. So we're going to spend some time with that today, or this next few days. I have a couple more little definitions that we need to write down. Actually, only one, really. We already defined amplitude, didn't we? Should we write it down one more time since it was in your notes that you turned into me? What is amplitude?
The angle.
It can be measured in an angle, but it's not always measured as an angle. What is it?
It's like how far.
Displacement.
Rihanna, what'd you say?
Distance or displacement.
Yes, and it's not just any distance or displacement. It's the biggest one. It's the maximum. Because, just to be really clear, if you're watching this, guys, please, there is too much talking. My little brain can't take it right now, so please stop. If I release it from here, this is its amplitude. That's its maximum distance away. If I release it from here when it's here, it's not at its maximum displacement. So that's not its amplitude. The maximum displacement is the farthest away that it can go. Okay? So maximum displacement from equilibrium. It's marked with the letter A, and it is usually measured in meters. In the case of our pendulums, we did measure it in degrees, but usually we measure it in meters. We also defined earlier this week period. And what is period? You guys measured it a lot.
It's a time that it takes from one object to travel distance and get back to the same place.
Yep. Time for one oscillation. Period is marked with the letter T, capital T, not with a P. What does P stand for? Power. Capital P is power. Yeah. Small p is momentum, you're right. And period is generally measured in seconds. The other one that we haven't yet written down but is also very important is frequency. Okay? So frequency is not a terribly complicated idea, but sometimes people get a little bit mixed up with it. So frequency, like if you think about whether or not you do something frequently, what does it mean to do something frequently? Right? So if I do something really frequently, it means I do it a lot, right? I do it very, very often. So if we talk about a spring bouncing up and down, it hits a certain point very frequently. How many times does it do it in a given amount of time? That's exactly what frequency is. It's the number of oscillations in the very general definition is in a given time. But generally that given time is 1 second. Okay. Frequency is marked with a small f. And then we have to figure out the units. It's a number of oscillations in a certain number of in 1 second. So kind of like for our friends the radians, right, where a radian is just a ratio, it doesn't really have a unit. The number of oscillations is just a number without a unit, so we kind of leave that one alone. So it's just we just need a placeholder, so like a 1 is a good placeholder. And then what's in the denominator? Number of oscillations in a second. So it's 1 over seconds. Sometimes we get lazy and don't want to write 1 over seconds. Frequency is measured in 1 over seconds. It's also measured in, does anybody know? My musicians may know. Hertz? Yeah. It's in hertz. HZ. And the measurement of hertz literally is just number of cycles per second. That's all it is. Okay? So if you like 1 over seconds better, awesome. If when you're solving a problem, you have something in hertz and you're trying to cancel it out, you need to remember that hertz is equal to 1 over seconds. Okay? That's an important deal. Questions so far? We okay? Okay, I've got 3 questions I want to ask you. 3 conceptual questions. I'm going to let you read all of them, come up with answers to all of them by yourself first. So this is quiet time, you and your brain. I'm going to give you just a few minutes to read through all of them, to write down. You don't have to write down formal answers, but just quick answers. Then I'll let you discuss, okay? So quiet time for a couple minutes here. I'm going to make a suggestion for question 2, because a lot of times in what we've been thinking about either a pendulum, which does exhibit simple harmonic motion, or we think about it as a mass on a spring up and down like this, which gets a little confusing. So I'm just going to introduce you to a mass on a spring that is going horizontally. Just makes life a little easier, I think. So there's your spring. It's a frictionless surface. And then here's your mass on the spring, okay? And I'm going to put this as my equilibrium position. So this is x equals 0. And then you could maybe think about which way the forces are acting, which way the displacement is happening, etc. So I just want to introduce that to you so you kind of see it, because it might be helpful as you're talking through this. And are you guys ready to talk about number 2, or do you still, it sounded like people were still chewing. One more minute?
Time to talk, or like, do you need us to get going, or?
Well, ish, but I also want to make sure you understand it and feel like you have had a chance to talk about it.
I think we're good.
Okay.
What'd you give?
All right, Elizabeth, what'd you guys say back there? Did you come up with an answer? Yeah. You picked C. What do you guys think? Do you agree with her? You had C initially, but you don't necessarily, you're not convinced anymore? Can you tell? Okay. Can you tell me, like, you had C initially, you're not so sure? Oh, okay. Where are you at right now? Or do you don't have an answer right now? Now you think it's A. Okay, but you're not gonna like bet the farm on it. Okay. Henry, go.
I said B.
Okay. So now we've got all 3 answers as possibilities. Do you want to make an argument for it?
Yeah, I remember a couple units ago that you said the X and the Y never like are the same or something like that. I don't know. I just remember from a couple units ago. But I don't remember what they said.
Okay. Could be. I don't remember. I don't know what the context was, so I can't say that I didn't, but I don't know if I did or not. Okay. Somebody want to make an argument, I guess, for any of the 3? Go, Rihanna. What you got?
We were thinking about C, is that if you push it back, the position is going to be this, but your amplitude is always, your acceleration is always coming back towards the center. So no matter what side, it's always facing away from the direction.
Okay, so let me see if I understand. So you're going to push it back to here, is that right?
Yeah.
And if you push it back to there, then you're saying that your displacement is negative? If we call that like the negative side, is that kind of what you're saying?
Yeah.
And if you do that, then what force is acting?
Then it's going to push back.
It's pushing back this way, right?
But is it the acceleration when it's released, or the acceleration to the displacement?
Nope, it's oscillating. So as it's oscillating, is it possible, or which of the 2 cannot be in the same direction? So you're saying the force is going to be in this direction? And if the force is in that direction, that's not the question. There are no answers with force. So
No, the acceleration will go back towards the center.
because force is going to be mass times acceleration, right? I just want to make sure that we're all making that connection. So this is the net force acting on it going back this way, okay? So the acceleration is going in the positive direction while the displacement is going negative. So in that one particular case, that's true. What about other cases? Are there other cases in which that same thing is true? What if I pull it the other way? If I pull it out like this and I put the box here, now its displacement is positive. And which way is its force going?
Negative.
In the negative direction, which means the acceleration is also negative. Is there any case in which the displacement and the acceleration will have the same sign? Or what did it say? Can't both be in the same direction. Yeah.
At equilibrium.
At equilibrium, what is the acceleration? And what is the displacement? So do they have a direction? So it's kind of like a null set, right? If they're both, but yeah, so we can fight that a little bit. Yes, true. So that you were arguing for C.
Yeah.
Is it possible for the position and the velocity to be in the same direction?
Yeah.
Yeah? When?
Once it's like
past equilibrium.
When it's going, right? So like if we pull it back to where it's pink and it's moving this direction, once it passes here, it's moving this way and its displacement is this way, so they'd both be positive, right? Is it possible for the velocity and the displacement to be opposite? Yeah, on the way back, right? Yeah. So that's really, we're going to get into that a lot tomorrow, so I want to make sure that that makes sense. Oh my gosh. The bell's going to ring in like 5 seconds. So we'll do number 3 tomorrow. Does that sound okay? We'll talk about it. I don't want to tell you the answer. That would be terrible.
D.